Right now, 13 billion miles from where you are sitting, there's a machine older than most of the people watching this video, moving through a region of space that no other instrument built by human hands has ever measured directly. Not inferred, not calculated, measured. And what it found there did not just add a footnote to what we already knew about the edge of our solar system. It contradicted the very spacecraft that made headlines for doing it first. This is the story of Voyager 2, the twin that everyone forgets, the one that quietly did something its more famous sibling never could, and the one whose discoveries are, right now, in the summer of 2026, about to determine whether either spacecraft survives long enough to keep talking to us at all. Stay with me, because by the end of this you will understand something about our solar system that most textbooks still get wrong, and why the next few weeks may decide how much longer humanity keeps a living voice in interstellar space. Everyone knows Voyager 1. It is the record holder, the farthest human object ever built, the one that carries the golden record, the one that crossed into interstellar space back in 2012, and has been making headlines ever since. But there is a second machine out there, moving through a completely different patch of the galaxy in a completely different direction, and for 6 long years, it was doing something Voyager 1 could not do at all. It was preparing to measure the one thing that actually matters, most at the edge of our solar system, and it was going to do it with an instrument that had already died on its twin decades earlier. Here is the part of the story almost nobody tells you. Voyager 1's plasma science instrument, the device built specifically to measure the temperature, the density and flow of charged particles both inside our solar system and beyond it, stopped working in 1980. Not at the edge of the solar system, not in interstellar space. In 1980, before the spacecraft had even finished its flyby of Saturn, 4 decades before Voyager 1 crossed into interstellar space, the one instrument that would have told us most clearly what that crossing actually felt like had already gone silent. For the entire span of Voyager 1's historic 2012 crossing, and for every year since, scientists have had to reconstruct what was happening to the plasma around it indirectly, through other instruments, through models, through inference. They never got a direct reading. There was a hole in the data, and for over 3 decades nobody could fill it. Voyager 2 launched 16 days before Voyager 1, on August 20th, 1977, and despite carrying the lower number in its name, it was sent on a longer, more complicated path, where Voyager 1 rushed past Jupiter and Saturn and then angled sharply out. Of the plane of the solar system to speed toward interstellar space, Voyager 2 was given a route that let it do something no other spacecraft in history has ever repeated. It visited all 4 giant planets, Jupiter, Saturn, Uranus, and Neptune, one after another, using each planet's gravity to sling itself toward the next. It is still, to this day, the only spacecraft that has ever flown past Uranus or Neptune up close. During its 1986 flyby of Uranus, it discovered 10 previously unknown moons and 2 new rings, and measured a magnetic field so strangely offset from the planet's spin axis that scientists are still trying to fully explain it. During its 1989 flyby of Neptune, its last planetary encounter, it discovered 6 new moons, clocked winds racing at 2,400 kilometers an hour, the fastest ever measured anywhere in the solar system at the time, and photographed active nitrogen geysers erupting from the surface of Neptune's moon Triton. Not a world, it revealed, was almost certainly a captured object from the distant Kuiper belt rather than something that formed there naturally. All of that alone would make Voyager 2 one of the most productive machines in the history of space exploration, but the price of that longer, richer tour was time. While Voyager 1 was already deep into interstellar space, already rewriting the textbooks, Voyager 2 was still years away from the boundary. It did not cross the heliopause, the true edge of our solar system, until November 5th, 2018, more than 6 years after its twin. For 6 years, Voyager 1's data suggested something strange and unresolved was happening at that boundary, but the story from the spacecraft that got there first was incomplete, because it was missing exactly the instrument needed to complete it. Voyager 2 still had that instrument. 41 years after launch, exposed the entire time to the harshest radiation environment a human-made object has ever endured. Its plasma science instrument was still alive. And when Voyager 2 crossed the heliopause, that instrument did something Voyager 1 never managed. It captured, for the first time in human history, a direct simultaneous measurement of plasma on both sides of the boundary between our solar system and the space between the stars. What it found did not simply confirm what Voyager 1 had already told us. In several critical ways, it complicated it, and in some ways it flatly contradicted it. 5 separate papers, published together in the journal Nature Astronomy in November of 2019, laid out findings that stunned a community that had spent 6 years building its picture of the heliopause out of half the necessary data. The first surprise was about the shape of the boundary itself. Scientists had expected the heliopause to be a relatively thin, sharp line, a narrow zone only a few 100,000 kilometers wide, where the hot solar wind ends and the cold interstellar medium begins. What Voyager 2 actually measured was a transition layer roughly 100 million miles wide, sitting just outside the true boundary, in territory that was supposed to already be interstellar space. Inside that layer, instruments detected interstellar particles that had pushed inward through the heliopause, like roots pressing through rock, extending more than 100 million miles into what should have been purely solar territory. Voyager 1 had seen hints of something similar on its own approach, a stagnant region where the outward solar wind seemed to run out of momentum, but the structure Voyager 2 measured on its own approach, from a completely different direction, looked meaningfully different in its plasma properties. 2 spacecraft, 6 years, and 1 entire solar cycle apart, crossing at different points around the same boundary, and finding 2 boundary structures that did not match. Then came the distance itself, which turned out to be one of the most quietly unsettling numbers in the entire dataset. Voyager 1 crossed the heliopause at a distance of roughly 121.5 astronomical units from the Sun. Voyager 2 crossed at roughly 119 astronomical units. Those 2 numbers are almost identical, and that should not have happened. Voyager 1 made its crossing near a period of high solar activity, when the Sun's output and the pressure of the solar wind were strong, which should have pushed the boundary of the heliosphere outward, making it larger. Voyager 2 crossed years later, near a period of low solar activity, when the solar wind was weaker, which should have let the boundary shrink inward. Instead, the 2 crossings landed almost on top of each other. One of the lead scientists on the Voyager mission, a researcher at Johns Hopkins named Stamateos Krimigas, said it plainly in the aftermath of the findings. "We do not understand why that is. That is not a small admission." That is one of the most senior scientists on a 50-year-old mission, stating on the record that something basic about how the size of our solar system relates to the Sun's own activity does not behave the way the models predicted. The third finding concerned temperature, and it may be the most quietly dramatic of them all, because it came from an instrument Voyager 1 simply did not have anymore. Scientists had long theorized what the interstellar plasma beyond our solar system should be like: cold, thin, quiet by comparison to the furious solar wind inside the heliosphere. Voyager 2's plasma instrument gave us the first direct measurement ever taken of that plasma from inside it, rather than estimated from theory at a distance. The interstellar plasma turned out to sit somewhere between 30 and 50,000 degrees Kelvin. Hot by ordinary standards, but dramatically cooler than the tens of millions of degrees measured just inside the boundary. The contrast was sharper than predicted, and more importantly, the actual baseline temperature of interstellar space, the number theorists had been estimating for decades without ever measuring it directly, turned out to be off by roughly a factor of 2. 2. Not a rounding error, not a minor correction. An entire baseline physical property of the space immediately outside our solar system, wrong by half, until Voyager 2 finally went there and measured it for real. And then there is the finding that Ed Stone, the Voyager project scientist at Caltech, who held that position since before either spacecraft even launched, Abbas personally singled out as the most remarkable result of all. The heliopause leaks. Not metaphorically, literally. The boundary that separates our solar system from interstellar space is not a sealed wall. It is porous in both directions. Voyager 1, approaching from the north, had detected what looked like tendrils of interstellar material pressing inward through the boundary before it even crossed. Voyager 2, approaching from a different angle entirely, detected the opposite effect on its own approach. A slow trickle of low-energy solar particles leaking outward into interstellar space before the spacecraft had even reached the boundary itself. 2 spacecraft, 2 different directions, 2 different mechanisms, the same underlying conclusion. Material crosses this boundary constantly in both directions, all the time. Stone summarized what this meant for our basic understanding of where our solar system ends and the galaxy begins, and he chose his words with obvious care. He said the 2 Voyagers are showing us how our sun interacts with the material that fills most of the space between stars and the galaxy, not where the sun ends, how the sun interacts with what lies beyond it. That is an entirely different, far messier, far more dynamic picture of our cosmic neighborhood than the clean boundary line most of us grew up seeing in diagrams. Why does any of this actually matter to you, sitting wherever you are right now, with no plans to ever travel past Neptune? Because the heliosphere, this vast bubble the sun blows around our entire solar system, functions as a shield. It deflects a significant portion of the high-energy cosmic radiation streaming in from distant exploded stars, a radiation that would otherwise reach the inner solar system, including Earth, at much higher intensity. Voyager 2's data tells us that shield is not a clean, static wall with a fixed size that simply grows and shrinks predictably with the sun's activity. It is a leaky, structurally uncertain, dynamically behaving boundary whose size does not track solar output the way every model assumed it would. We are only beginning to understand what that means for the long-term stability of the very shield that has helped protect the biosphere of this planet for billions of years, And the honest answer right now is that scientists do not fully know. Now, here is where the story becomes urgent, because this is not simply a historical account of what Voyager 2 found back in 2018. This is happening right now, in the summer of 2026, and the outcome of what happens in the next few weeks will determine how much longer this unique, irreplaceable window into interstellar space stays open at all. Both Voyager spacecraft are running on power supplied by radioisotope thermoelectric generators, essentially containers of decaying plutonium-238 that convert heat into electricity as the plutonium slowly breaks down. At launch, each spacecraft had roughly 470 watts of power available. Today, nearly 50 years later, that output has fallen dramatically, and it keeps dropping by about 4 watts every single year, a slow, mathematically certain decline that cannot be reversed, only managed. Voyager 2 currently has slightly more power available than Voyager 1, which is why it still has 3 operating science instruments: its plasma science instrument, its magnetometer, and its plasma wave subsystem, while Voyager 1 now runs with only 2, after its low energy charged particle instrument was switched off earlier this year, simply because there was no longer enough power to keep it running. To try to buy more time, the engineering team at NASA's Jet Propulsion Laboratory has developed an experimental procedure they have nicknamed internally the Big Bang. It is exactly as dramatic as it sounds. Rather than adjusting the spacecraft's power distribution one small step at a time, testing each change before moving to the next. The Big Bang reconfigures a whole group of powered systems simultaneously in a single coordinated operation, switching some things off and replacing them with lower power alternatives all at once. The reasoning is that any power reconfiguration passes through unstable intermediate states, moments where the system is neither in its old configuration nor its new one, and those unstable moments are exactly when a spacecraft's automated fault protection systems are most likely to panic and start shutting things down on their own to protect against what looks like a dangerous power draw. Doing everything at once is meant to get through that dangerous window as fast as possible, minimizing the time spent in a state that could trigger an automatic shutdown nobody intended. This is being tested right now on Voyager 2 first, not because its data matters less, but because it currently carries slightly more power margin and sits somewhat closer to Earth, making a communication delay of a little over 16 hours each way marginally less punishing than the 22. Hour delay facing Voyager 1. Every single command sent to test this procedure has to travel that entire 16-hour journey before it even reaches the spacecraft, and every response takes another 16 hours to come back. A single round of communication, one command and one confirmation, costs more than a full day. There is no way to speed that up. There is no backup spacecraft. There is no second attempt if the fault protection systems get confused mid-reconfiguration and start shutting down instruments, so that might never come back on. This is being done once, carefully, deliberately, by a small team of engineers working with documentation and programming conventions from an era before most of them were even born. If the procedure works cleanly on Voyager 2, the same reconfiguration is expected to be attempted on Voyager 1 no earlier than July of this year, potentially even allowing the recently shut down low-energy charged particle instrument on that spacecraft to be switched back on. If it does not work cleanly, if something goes wrong during that one uninterrupted attempt, there is no guarantee either spacecraft's remaining instruments survive the failure. This is not a metaphorical high-stakes moment invented for dramatic effect. This is an actual engineering decision, happening in real time, that determines whether the only 2 functioning instruments that have ever directly sampled interstellar plasma keep transmitting or go quiet years earlier than they otherwise might have. And there is no replacement waiting in line. There is no other spacecraft anywhere near the heliopause. There is no funded mission currently designed to reach interstellar space and repeat what these 2 machines have done. If a new mission capable of crossing the heliopause were approved and built starting today, it would not arrive at that boundary for at least 25 years. Whatever open questions Voyager 2's data raised about the leaking boundary, about why the heliosphere's size does not track the solar cycle the way it should, about the true structure of the shield that protects our entire solar system from the radiation of the wider galaxy, those questions will simply sit unanswered the moment these 2 spacecraft finally go silent. The map they have been quietly drawing for nearly a decade will stop being updated, and it will stay frozen in place for at least a generation. So here is where we actually stand, right now, in the middle of 2026. 2 machines, each about the size of a small car, each running on less electricity than the light bulb in your refrigerator, are sitting on opposite sides of our solar system's true edge, in a place no other instrument has ever directly measured, sending back data that has already forced scientists to admit, in their own published words, that they do not fully understand why our solar system's protective boundary behaves the way it does. One of those machines is currently undergoing an untested, irreversible power reconfiguration that will decide how much longer it keeps talking to us. The other is waiting to see if that same risky procedure will be attempted on it next. Nobody currently alive was working in aerospace engineering when these spacecraft launched using the conventions their control systems still require. When the engineers who understand this specific, decades-old spacecraft language eventually retire, that knowledge does not transfer easily to a new generation because nothing quite like it has been built since. Voyager 2 already gave us something Voyager 1 never could, a direct, simultaneous, undeniable reading of what actually happens at the true edge of our solar system. And it complicated almost everything we thought we understood about where our sun's influence ends and the galaxy truly begins. Whether it gets to keep giving us more of that story depends on a procedure being tested right now, 13 billion miles away, across a communication delay longer than a full-day round trip, with no second chance if it fails. The signal is still coming, for now. If you want to know what happens when the results of this procedure come back, and what it means for the future of both Voyagers, subscribe and turn on notifications, because this story is still being written in real time, and you will want to have already understood it when the answer finally arrives.